And now for advanced beer pong. We're at the same party. Okay, so we've got a cup 0.2 or 20 centimeters high, 1 meter away, but now a frat boy is throwing the ball. And he's throwing it from 0.6 meters because he's, a little bit taller. And he's throwing it at 5 meters per second because he's a frat boy. See, my narrative is consistent here. And he also wants to land it in the cup. And the question is, if he really has to throw it at 5 meters per second, what angle should he throw it at? That's what we're going to solve. So here is my advice to you. If VI or theta is, what's the word I'm looking for, is left variable, is unknown, use R. So in beginner's beer pong, I said this is a case where you don't want to just write out the R vector. You want to just kind of solve it by breaking it in half. But when these are unknown, R. Okay? So we'll do it the proper way. We will write the position vector R of the ball. Right? We just need the x component. Well, x component is constant velocity motion, no acceleration, so it is simply 5 cosine theta t. No initial position I hat, right? Because it started at 0. There's the origin. And the y component. The y component did start at 0.6. It has an initial velocity 5 sine theta t. And of course in the y, it's accelerating down minus 1/2 gt squared, or minus, I'll save myself some math, 4.9 t squared. That's 1/2 of gravity, 4.9. All right. So now what you can do when you have something like this is you can say it must be at x equals 1, y equals 0.2 at some time. So we just have to solve these in this case, and I'll probably call it t star since it's a specific time. So for example, 5 cosine theta, a specific time t star, has to be equal to 1 meter. And at the same time, y, 0.6 plus 5 sine theta t star minus 4.9 t star squared has to be equal to 0.2, the height of the cup. It has to be right here at 1.2 at time t star. So what we have here is 2 equations. All right, there's an equation, and there's an equation, and 2 unknowns. We don't know theta, and we don't know t star. Of course, what we want to solve for is theta. So in this case, it looks bad. It's not as bad as it looks. We're going to solve this one for t star. T star equals what? 1 over 5 cosine theta. And we're going to plug that into there. So what do we get? 0.6. I'm going to go ahead and bring this 0.2 over. So this 0.2 is going to come over here. I'm going to get 0.4 plus, let's see, this is going to, the 5 over 5 is going to cancel. Sine over cosine is tangent theta. So when you plug that in there, you get just tangent theta. Promising. And then you say minus, now we got 4.9 over 25 cosine squared theta. 4.9 over 25, that's about 5 over 25, that's about 0.2. So this one is minus 0.196, close to 0.2. And then we just have this 1 over cosine squared theta in the bottom, times 1 over cosine squared theta. Sorry. Too much beer pong. There we go. Equals 0. All right. And that looks pretty hopeless. We got to solve this for theta. We got rid of the t star. Got to solve that for theta. Well, sometimes when it looks hopeless, you got to go to your trig identities. Right? So there is a trig identity, and you could prove it to yourself pretty easily, actually. That 1 over cosine squared theta is equal to 1 plus tangent squared theta. And if you don't believe me, just think, what if we multiplied through by sine squared, or by cosine squared? If we multiply this through by cosine squared, this would be 1 equals cosine squared plus sine squared, right? Sine over cosine, which we know, sine squared plus cosine squared is 1. So it's really just a modification of that. So if we're going to use that, what that means is, we're going to turn 1 over cosine squared theta into 1 plus tangent squared theta. So this is going to become 1 plus tangent squared theta, which means we're going to have 1 times 0.196. So that negative 0.196 we can combine with the 0.4. Okay, so the constant terms are about to change to 0.204. Okay, I'm not messing with that term, plus tangent theta. And then the squared term was this is minus 0.196, and then this part. Minus 0.196 tangent squared theta equals 0. Okay, and now that is a nice little quadratic equation, right? Tangent squared theta, tangent theta to the 0. So even though it's tangent rather than x or y, you can still solve it, quadratic equation. And what you'll get if you do that, so you go, oh my God, I could write it minus 1 plus or minus the square root of b squared 1 plus 1.6 is the minus 2ab over 2a is whatever it is, over 2a is minus 3.392. What you're going to get is that theta, of course, has two values, right? There's a plus or minus in here, so you get that theta equals either 81.5 degrees or it equals negative 57 degrees. Okay? So when you get two answers in a physics problem, sometimes one of them is meaningless, and sometimes they actually both work. So let's look at this case. What do we think it is? It could be 81 degrees above the normal. You got to throw it at a huge angle. That seems all right. But maybe the negative 57 is also right, because you could throw it like that. So in this case, both answers are actually correct. So first, let's see the high answer. Does that really work? Let's see what can happen here. So frat board, we're going to throw it really hard. Throw it up and up. Oh, no. Oh, I forgot the rules. High angle. We got to get the high angle. This is not over. See that? You see that? Oh, man. It was, I don't know what that was. Something weird. So at the high angle, it will go in, as you can imagine. You just got to get the hang time right for the thing going down, right? The low angle. Can the low angle go in? I don't need this. I'm just going to nail it. Oh, I'm not. Oh, 57 degrees. I thought it was 37. I was, 57. Oh, here we go. Okay, this is the last one. So this has to go, or I'm just going to cancel the whole class. We're now going to do the most famous demonstration in all of introductory mechanics, the hunter and the monkey. In this demo, I will play the hunter, of course. And for the monkey, we wanted to get a live monkey, but after 102X and the dead cat, we got a lot of phone calls. So we're going with this fake monkey. So here's the monkey, fake monkey, not alive. Everything will be fine. And before we do the demo, of course, we have to talk about the physics, right? That's actually the fun part. So the hunter is over here, and I'm not going to wear the hat, of course. And the hunter has a gun, and he's going to shoot the gun. So the bullet is going to have an initial velocity like that, v0. And he shoots it, and he aims right at straight line, looking through his sights, right at the monkey. So here's the monkey, and it's sort of holding on to a branch. Here he is, like that, and the branch is in a tree like this. There's the tree, like that. There we go. Aimed right at the monkey. Now, we need a few parameters here. So here's, let's say, the ground down here. So we need to know this distance, the distance horizontal from where the bullet starts to where the monkey is. So that's kind of like the x component, d. And we need to know how high the monkey is relative to the bullet. So we'll call that h. So the distance and the height. And the, let's see, so yeah, he has aimed his gun where he should hit the monkey. He has it at some angle theta, gives it some velocity. Okay, so now, to figure this out, first we got to go with the story. We need a narrative here, right? So what's going to happen? The hunter shoots, exclamation point. What do we hear? We hear a bang. Bang, very loud, right? So what happens when the monkey hears a bang? Freaks out. You ever seen a monkey freak out? It's scary. Okay, he's going to freak out, he's going to let go, and the monkey drops. Oh no, the monkey's going to fall. It's okay though. And the question really is does the hunter's bullet hit the monkey? All right, that's the question we come down to, is do we have a hit? All right, so there is the story of the demo. He aimed right at the monkey. He shot, the monkey dropped right when he shot. Does he hit it? Okay, so this is a trajectory problem, clearly. It's sort of a two-body trajectory problem. The bullet's going, the monkey's going. And the best way to approach these, I think, is simply to write down the position vector. That's what I keep saying for all of them. We're going to write the position vector for the bullet and the position vector for the monkey under the case of constant acceleration. Constant gravitational acceleration down, no acceleration in the horizontal. So let's do that. So here is the position vector, RB, of the bullet. Its x component, it has no initial x position. We'll assume that this is the origin. Say that's the origin down there. So 0 position, it has an initial x velocity, v naught cosine theta, times time. All right, so it starts out at 0. V naught cosine is the horizontal component times time. And that's all it has in that direction. All right, there's no acceleration in the horizontal. In the vertical, let's see, it has 0 offset. It has v naught sine theta t, that's its initial y velocity, and it does drop at 1/2 gt squared in the y, because gravity pulls down the bullet, right? J hat. All right, now let's write down the position vector for the monkey. So the monkey's x position starts out at d, and the monkey has no x velocity, it just falls straight down. The monkey has no x acceleration, because there's no reason for there to be one. So the monkey's x position is simply d. D times I hat. Okay. The monkey's y position is what? Let's see. The monkey's y position, the initial y position of the monkey is h. Starts out at h. Let's see. And then his initial velocity is 0. And he accelerates down as he falls. So minus 1/2 gt squared. Where I'm putting a minus because we're assuming g is a positive number, 9.8. And that's in the j hat. So that's how I always like to do these problems. I like to write out the full expressions for the position, because we know we can get everything from these, velocities, accelerations, etc. Okay, but then the question is, do they hit? Right, that's really what we need to solve for, is are they going to hit? The way to ask that is, does RB position equal RM position at any time? If they hit, they have to be in the same place at the same time. So in a way, we really just have to equate these two and say, is there a time where that is true? Okay? So let's do it first by just equating x and equating y and see if there's any time where the x components will be the same and the y components will be the same, just to avoid all the vector notation. So let's see, is there a time when v naught cosine theta t, and I'll say t star because we're looking for a specific time, equals d, right, the bullet equal the monkey, and is there a time when v naught sine theta t star minus 1/2 gt squared equals h minus 1/2 gt squared? And these are all t stars. Is there such a specific time when those are both true? Well, one thing you'll see is, oh, well, they both have this term. That goes away. That's a hint to the answer, right? There's gravity terms cancel. So then we're left with, is there a time when v naught cosine theta t star equals v naught sine theta, or I'm sorry, when v naught cosine theta t star equals d and v naught sine theta t star equals h? Is there ever a time when that is true? What would it take to make that true? For that to be true, we could solve for t star and set them equal to each other and see what the requirement is. Okay, so let's look at that. If we solve this for t star, it would be v naught cosine theta over d. V naught cosine theta over d. That would have to be equal to this t star, which is v naught sine theta over h. V naught sine theta over h. So really then, the answer is the hunter will hit the monkey if that is true. And that looks weird. How can we do with that? Well, we can cancel the v naught. Okay, I did that step. Now what would you do? We could put the sine over the cosine and call it tangent. That's popular. All right, so let's say tangent theta equals h over d. So we would say this is the condition that's required for the bullet to hit the monkey. Well, is that what we have here? It is. Look at this triangle right here. Here's theta, here's h, and here's d. What's the tangent of theta? H over d. This is the condition you need for the hunter to be aimed right at the monkey, is that the tangent theta h over d. So according to kinematics, it seems like it will hit. Right? And according to your intuition, it will probably hit. You know that this bullet is going to drop due to gravity. And you know this monkey is going to drop due to gravity. They're going to drop the same amount due to gravity. That's what happened when these two terms just went away. So you take those terms away, and sure enough, they're going to hit. In fact, the monkey has to drop. If you shoot and the monkey doesn't drop, the bullet would go under. Right? It's actually critical that the monkey freaks out and lets go. So let's see if it's true in the real world. We're going to come around here and shoot the gun. Monkey will drop at the same time. So here at Rice, we like to give the monkey a sporting chance. So we actually shoot him with a blowgun. So here is the blowgun set at the right angle. And then over there, the monkey is hanging from the tree with an electromagnet. So what we need to do is to aim it just right, look in here and make sure that we see the monkey straight down the tube of the blowgun. And there he is. These are the bullets for the blowgun. And this little clip on the end is a switch that breaks the electromagnet. So when that pulls up, the monkey falls. So you're going to see that happen when I put the bullet in. All right, so I'll pull it up, and I'll go ahead and put the bullet in and push it to the back like that. So now, when the bullet flies out, the monkey's going to fall again. Let me go set the monkey up again. All right, everything is set. We've got the gun, the bullet, the switch, and the monkey. Now, I just attach this highly sanitary tube to blow into, like this, like that. And I take this end, and here we go.